All right. Lastly, we're going to look at two geometric applications of hyperbolas. Now, these applications end up being a little bit more complicated and involved. So we're not going to be going through any particular problems involving these, but I just want to show you where hyperbolas come into play in very real life situations. So the first is a particular type of telescope, and this telescope actually uses two different conic sections. So inside many telescopes, there are two different curved mirrors. One of them is parabolic, so it's like a parabola, and then the other one is hyperbolic, so it's like a hyperbola. And these mirrors work in parallel. They work together. So this parabolic mirror on this side, we know that parabolas take waves, in this case light waves, that are coming directly in, perpendicular to the directrix, and they reflect them all towards a single point, which is the focus of the parabola. So actually the focus of this parabola is somewhere over here. So what's happening is this parabola is taking the light waves that are coming in parallel and to each other, and it's reflecting them all towards one focus over here. But then we have this hyperbolic mirror. Now we know that hyperbolas, this is just a small part. The hyperbola would be branching out this way, and in fact there'd be a whole second branch to the hyperbola on the other side, but it's just one little bit of one of the branches of the hyperbola. Now the reflection property of a hyperbola is such that any light waves, or sound waves, but in this case light waves, any light waves that are heading directly toward one of the foci get reflected, and the direction they get reflected in is the other focus, the other focal point. So in this case, that would be where your eye would be if you were looking through this telescope. And so what happens is these light waves, these light rays, hit the parabolic mirror, which reflects all of them in towards the other focal point. I'm going to draw a couple of these in. But then, instead of making it to that focal point, they hit this hyperbolic mirror, and the hyperbolic mirror, instead of having them go towards the one focal point, reflects them instead to the other focal point of the hyperbola, which is where the viewer's eye is. And so this allows us to take all of this information, all of the light from outer space, whatever we're viewing, and it gets reflected specifically to where the viewer's eye is. So you can actually read a little bit more about this online. This is just a very basic explanation of how it works. If you're really interested in this, you can read up a bit more. But we often will find parabolic and hyperbolic lenses in different telescopes and things like that. So they're very, very useful in that sense. The other example I want to look at actually involves whales in the ocean. And I first learned about this when I was on an expedition trip to the Ross Sea, which is basically the part of Antarctica. We went down towards Ross Island, which is where one of the largest research stations in Antarctica is. We saw emperor penguins. We did see some whales. It was an amazing trip. But one of the things that I learned was that hyperbolas are used when scientists are trying to locate whales in the ocean. Now, to understand how this works, we actually need to go back to the geometric definition of a hyperbola. We're not actually going to use the reflective property here, we're going to use the geometric definition of a hyperbola. So what I'm going to do is I'm going to draw in the two foci of a hyperbola, and I'm going to remind you that a hyperbola is the set of points such that the distance between any point on that hyperbola and the two foci, those two distances have a common difference. And so I'm just going to draw in one branch of the hyperbola here. So using the definition, any point on this hyperbola, if we look at the distances between that point and these two foci, the difference is going to end up being constant. And that's actually what's going to come into play here. So what scientists do when they want to locate whales in the ocean, to see how many whales there might be in a certain area, instead of just doing it by sight, they will get multiple ships in the water. In this case, we've got 2 ships at the 2 foci, but we're going to need a third ship, and I'll explain why in a minute. So they get 2 ships in the water, and they get microphones that they put underwater, and they record the sounds that they hear of the whales. And they have to make sure that they've synchronized the times between the recordings, because what they can do is they can compare the recordings and see what the time difference is between when one of the microphones picked up a certain whale's noise and when the other microphone picked it up. That time difference can then be used to calculate a difference in distances between the whale and the 2 different ships based on how quickly sound moves through water. And when they calculate that, they can figure out the difference in the distances between the whale and those 2 ships. And what that does is it gives them a hyperbola that the whale must be located somewhere along. And specifically, they can narrow it down to one branch of the hyperbola instead of the other. I'll draw in another branch really quickly. And they know which of the 2 branches it is because whichever one of the microphones picks up the whale's sound first, it's going to be on that branch because we know that it's closer to that ship than the other one. So if scientists have 2 ships in the water with 2 microphones recording these whale sounds, they can go through and do the math and figure out that every whale has a different sound, a different noise that it makes. So there might be 30 different whales that they hear on the recording, and for each one of these whales, they can put it on a certain hyperbola. But they need a third ship, because if they get a third ship in the water as well, what they can do is they can look at the difference between the sound timestamps on those 2 ships. Instead of the first pair of ships, they can look at one of the other pairs of ships. And what that does is they can look at the time difference, they can convert that into a difference in distances, and then they can look at the hyperbola that's created with those 2 ships as the foci. And once they have multiple hyperbolas, they can look and see where those hyperbolas intersect, and they can tell that that is the location of one of the whales. So what they do, and this has been done before, you can actually look up research studies online that go through the math and everything. And they use these recordings, they figure out how many whales they can hear on the recording, and they can pick up sounds from 50, 100 miles away, even further, because whales' sounds travel so far in water, and they can do the math between these recordings for each individual whale, and they can plot each whale's position in the ocean using this method. So they can get an idea of how many whales are in the vicinity by listening to the recordings and figuring out how many different whale sounds they hear. And they can use the timestamp differences to figure out where all of these whales are located, how many of them are located together in one group, how many of them are in another group together, etc. It's really an interesting use of hyperbolas that I had never heard of until I was on this expedition to Antarctica.